So in this problem, we have a fraction raised to a negative exponent. So the first thing I want to do is I want to get rid of this negative exponent by rewriting this as its reciprocal. So everything in the denominator, I'm going to move up to the numerator. And everything in the numerator, I'm going to put in the denominator. I'm not changing the signs of the exponents here, but I will change the sign of the exponent on the outside. That's going to become a positive 2. Once we move everything from the top to the bottom and the bottom to the top, we could simplify. I'm going to move all of these up top. So by moving them past the fraction bar, it changes the sign of the exponent. So this negative 3, when I move it up top, will be plus 3. So really what I have up top now is 2x to the 7th. This positive 5 will be a negative 5 up here. So I'm going to have y to the negative 6. And this z to the negative 1, if I move z to the negative 1 up top, that's going to be plus 1. So I'm going to have z minus 1, all to the positive 2 on the outside. And the only thing remaining down here is my 3. Now I could take my exponent on the outside and multiply it to the exponents on the inside. So it looks like I'm going to have 2 squared will be 4x to the 14th, y to the negative 12, z to the negative 2, all over 9. I don't like negative exponents, so to change the sign of an exponent, I could just move it past the fraction bar. So it looks like I'm going to end up with 4x to the 14th over 9, y to the 12th, z to the negative 2. My final answer. In this next example, we want to rationalize the denominator. So I want to multiply by the conjugate, which just means opposite sign. So if it's plus, we're going to multiply by rad 7 minus rad 2. Whatever we do to the bottom of the fraction, we have to do the same to the top. So we're going to multiply the top and the bottom by the conjugate. Up top, this is going to be a big FOIL problem. I'm going to distribute the 5 to both terms, and then I'm going to distribute the negative rad 2 to both terms. So I'm going to have 5 radical 7 minus 5 radical 2. Now I distribute the negative rad 2, so I'm going to have negative rad 14. Radical 2 times radical 7 is radical 14 plus rad 4, which will simplify to 2 in a minute. Here I'm multiplying conjugates. I know when I multiply conjugates, I could FOIL this out the same way, but since they're conjugates, I know that if I just multiply the first with the first, get rad 49, and the last with the last, get negative rad 4, I would have the same result as if I FOILed it. So now, this is actually, what is this going to be? 7 minus 2. So we're going to have 5 in the denominator. So it looks like my final answer, I'm trying to save some space here, is going to be 5 rad 7 minus 5 rad 2 minus rad 14 plus 2. Square root of 4 is 2, all over 5. I believe that to be the answer. In this next example, we're adding and subtracting radical expressions. So they're unlike radicals right now, but it looks like some of them could be simplified. So I'm going to have to simplify them. There, that was fast. So what did I do? I broke This first one, I see 18 could be broken up as 9 and 2, so I put my perfect square to the left and my remaining factor to the right. Under this radical, the radicand cannot be simplified, so I left it the same. Here I see 50 could be broken up as 25 and 2. X cubed could be broken up as x squared and x to the first. So I have all my perfect squares to the left, and now I could simplify this. So what do I have here? I simplified my radical 9 to a 3. And here I have the square root of 25 is 5. Square root of x squared is x. So now I simplified all my perfect squares that were under the radical. I could simplify this a little more because now I could do this multiplication. This is 15x. Right? This is going to stay the same. And 7 times 5 is 35x. And now I look at this problem, and they're all like radicals. So I can add them together. 15x minus 2x plus 35. Looks like I'm going to get 48x. Whoops. 48x rad 2xy. My final answer. In this next problem, it says simplify using properties of exponents. So they're fractional exponents, but it doesn't really make a difference. We want to take our exponent from the outside and multiply it to the exponents on the inside. So it looks like I'm going to have 125 to the 2/3. X to the, this is a negative 3 over 2 times 2 over 3. I multiply straight across. 2 times 3 and 3 times 2 gives me 6 over 6. Y to the third, that's like y to the 3 over 1. I do the same type of multiplication. My numerator to my numerator, my denominator to my denominator. So this looks like it's going to be 6 over 3. And then I'm going to have a z to the 2/3. I multiply the exponent on the outside to all the exponents on the inside. So really it looks like I'm going to have, let's call this 125 to the 2/3, x to the negative 1, y to the second, and z to the 2/3. 125 to the 2/3 really means the cube root of 125 squared. And the cube root of 125 is 5. 5 squared, this is going to give me 25. X to the negative 1, well, we know we can't have negative, so we're going to have to drop it to the bottom of the fraction. So I'm going to have x to the positive 1 on the bottom. Y to the second can stay up there. And z to the 2/3, if we wanted to write it as a radical, we would say the cube root of z squared, but that doesn't really help us. There's not a whole lot we could do with this one, so let's just leave it as z to the 2/3, and this is our final answer. 25y squared, z to the 2/3, all over x. In this next example, it looks like we're just adding and subtracting polynomials here. So we want to take what's outside of the parentheses and distribute it to all the terms inside the parentheses. We could even say there's a 1 here. So it looks like I'm going to have 5x squared minus 7x plus 11 minus 3x squared plus 16 plus 8x minus 15, right? So nothing changed except for when I distribute the negative, right? Negative times a positive is negative. Negative times a negative is a positive. So once I distribute to remove the parentheses, I could identify my like terms. All the x squares I'm going to put together. all the x to the first power I'll put together, and then all of my constants I'm going to put together. So 5x squared minus 3x squared is going to give me 2x squared. I have a negative 7x and a positive 8x. 8 minus 7 is 1x. So I could just write 1x or just x there. And then I have 11 and 16, which is 27. 27 minus 15 is a positive 12. Combine my constants, combine my first degree terms, then my second degree terms, and that's what it looks like in the end. In this next problem, it looks like I'm just foiling. I'm multiplying two binomials. So I'm going to take my first term and distribute it. Right? So that's going to give me 15x squared plus 5x. And then I could take my second term and distribute it. So I'm going to get negative 21x minus 7. Right? And then I can combine my like terms. So I have a positive 5x and a minus 21. This will come down 5x squared minus 16x minus 7. My final answer. In this next example, it looks like I have a binomial squared, 2x minus 7 squared. I could look at this two ways. I could say, well, this is really 2x minus 7 times 2x minus 7. And then I could FOIL it out. So I'm going to get 4x squared, 2 times 7, negative 14x, negative 14x plus 49. I'm going to combine my like terms, so I'll have 4x squared minus 28x plus 49. Or I could apply a formula, right? We know when I have a binomial squared, a plus b squared is equal to a squared plus 2 times ab plus b squared. Right? That just means this is my a term, this is my b term. So a squared, this would be 2x squared plus 2 times 2x times my b, which is negative 7, plus my b squared. So I would end up 2x squared is 2x times 2x, which is 4x squared. 2 times 2x times negative 7 is going to give me my negative 28x. And a negative 7 squared, negative 7 times negative 7 is a positive 49. So I get the same answer. This is a little bit shorter if you get familiar with the binomial squared and applying this formula. You could skip this step. It's my first term squared. I multiply these two and double it. And then it's my last term squared. Binomial squared. In this next problem, it looks like they're just asking us to factor out the GCF. So we want to see what they all have in common. It looks like they all are divisible by 4. They also all have an x to the first degree and a y to the first degree. So factoring out a GCF is really dividing all of these by 4xy. So 4 goes into 8 2 times. If I take an x out and a y out, I'm going to have 2xy squared, plus 4 goes into 25 times, and I have xy, if I take an x and a y out of there, x squared y, minus 4 goes into 12 3 times, and I take out an x and a y, so there's nothing left. So after I factor out my GCF, my answer looks like that. I could always check this by distributing it back in, if you want to check. Let's take a look at our next one. just asked to factor. This is a 4-term polynomial. We're going to factor this by grouping 2 plus 2. Here we could factor out the GCF over here. It looks like I could take out an x squared. And on this side, I could factor out a -5. After we factor out this first one and we get a remaining factor of x minus 1, we know that this also has to be x minus 1. Now I have to look for my GCF from this entire expression. They both have x minus 1. I could factor that out. I'm going to have x minus 1 times what's remaining is x squared minus 5. If this could be factored, we'd factor it further. If it was x squared minus 9, the difference of two perfect squares, we would have to go further, but in this case, we cannot, so we do not. Done. In this next example, we have 8x squared plus 33x plus 4. Our first step, even with the problem prior, our first step should always be to look for a GCF, a common factor. I don't see one here. This is a 3-term polynomial, trinomial. I'm going to factor by trial and error or reverse FOIL. What I put here and here has to give me 8x squared. 8x times x. And what I put here and here has to give me my 4x. So 1 times 4. My inners and my outers have to give me 33, and they do. 1x and 32x will give me the 33x. Anytime my C term is positive, it means my signs will be the same, and they'll be whatever my B term is. So in this case, my B term is a plus, so they'll both be pluses. And it has to check, right? A positive 1x and a positive 32x gives me my positive 33x. Positive 1 times positive 4 gives me 4. And 8x times x gives me x squared. So this works. Again, we have a 3-term polynomial, a trinomial. First thing I want to do is look for a GCF. And in this case, it looks like we have one. What goes into all of these? I see they're all even, so 2 goes into them all. And they all have a y in common. Looks like they all have y to the first. So that's going to leave me with 6x squared minus 7xy minus 5y squared. If I divide 2y into all of those, that's what I should get. This could be factored further. So let's say I'm still going to have my GCF of 2y, and then 6. I could use 6 and 1 or 3 and 2. I'm going to try 3x and 2x. And over here, what I put here and here has to give me 5y. So I could do 1 times 5 or 5 times 1. 5y times 1y. Because I can see that this is going to give me a 10. And my outers will give me a 3. And I know that 10 minus 3 is 7. I want a negative 7, so this has to be a negative 10 and a positive 3. Straighten this out. Okay, this one is a binomial also. It's not the difference of two perfect squares, obviously, because it's the sum, and there's no GCF. So I recognize this as the sum of two perfect cubes. So I could look at this as, this is really like 5x cubed plus 2 cubed, right? I know my formula, a cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. That's my sum of cubes formula. Everywhere there's an a, I'm going to put 5x, and everywhere there's a b, I'm going to put 2. So this would now read 5x plus 2, and then I would have 5x squared minus 5x times 2 for my a and b, plus 2 squared. Now, you don't have to write that all out. You could have done that in your head. So your final answer is 5x plus 2. 5x squared is 25x squared. 5 times 2 is 10, plus 4. That's my final answer, the sum of cubes. Once we apply the sum of cubes formula, this cannot be factored any further. It's prime, so you're done. In this next example, it's a 4-term polynomial, so we're going to factor by grouping. We would look for a GCF. There is no GCF. This is a special type of grouping because I recognize this as a trinomial squared. I could actually factor this as x plus 5, x plus 5 minus 36y squared. This is a grouping problem. I like to call it a 3 plus 1 because we're breaking up as 3 plus a negative 36 y squared. So now I have x plus 5, so this is really x plus 5 squared minus 36y squared. So I know this is a grouping 3 by 1 because not only do I have a perfect square trinomial here, I also have the subtraction of a perfect square over here. And what this does is it creates the difference of squares. It's the difference of two perfect squares. So just like we would factor our difference of two perfect squares, what I put here and what I put here has to give me x plus 5 squared. And what I put here and what I put here has to give me my negative 36, so plus 6y minus 6y. That's my final answer, right? X plus 5 plus 6y times x plus 5 minus 6y. And you could FOIL this all out, distribute your first term, your second term, and your third term, and you should come back to the original. Here you're asked to state the restrictions. So we want to factor the denominator. Once we factor the denominator, we want to, since these are restricted values, neither of these could be equal to 0. So we could create a statement saying x plus 9 cannot equal 0. X minus 5 cannot equal 0. Now if I subtract 9 from both sides, then x cannot equal negative 9, and x cannot equal positive 5. So my restrictions are x cannot equal negative 9 and x cannot equal positive 5, because if I substitute either of those into this expression, I'll get 0 in my denominator, which is an undefined value. And that's what I don't want. This next example is exactly the same. This is the difference of two perfect squares. So I'm going to have x squared minus 49. This denominator cannot be equal to 0. So I'm going to factor it. It's the difference of squares. So x plus 7, x minus 7. Right? So that means x plus 7 can't equal 0, and x minus 7 cannot equal 0. Therefore, x cannot equal negative 7, and x cannot equal positive 7. Or you could write that as x cannot equal plus or minus 7. In this next example, it looks like we have multiplication and division of rational expressions. So it's really multiplication and division of algebraic fractions. We know we can't divide by a fraction. We're going to have to change this to multiplication. We're going to have to multiply by the reciprocal, which means we change that to multiplication and we flip this. Or you might know it as keep, change, flip. But really we're going to do, we're just going to rewrite this as a multiplication statement by flipping this. So that's what I've done. All I did was flip this and change it to multiplication. And now what we could do is we could start factoring. I'm going to do this in 2 steps just to do it a little bit slower. The first thing I'm going to do is factor out all the GCFs. Right? So right here I'm going to take out what they have in common. So here it just has x. So I'm going to have x squared minus 25 all over 4x squared. So I'm going to do that for each one of these. Okay. In this next one, it looks like the addition of 2 fractions, addition of 2 rational expressions. So just like when I'm adding any kind of fraction, I always want to find an LCD. So in order to find an LCD here, I'm going to have to factor the denominator. So I could take out a 2, I'll have x plus 4. And over here, I look for what they have in common. As a 3, I'm going to have x plus 4. So I factor the denominators. Then I find an LCD. I want to find a value that both of these could go into. So if I look at my 2 and 3, I know 6. 2 and 3 could both go into 6. And in my LCD, I have to see everything here and everything here. This entire denominator has to be able to go into it, and this entire denominator I have to see goes into it. So I'm also definitely going to need an x plus 4. Right? 2 goes into this, and x plus 4 goes into this. 3 goes into this, and x plus 4 goes into this. So this is my LCD. My objective here is I want to see, I want these 2 denominators to be the same. So what I want to do is I want to multiply by a value that will make them my LCD. So over here, I want to multiply the top and the bottom by a 3, right? Because 3 times 2 will give me that 6. And on the right side, I want to multiply through by a 2. Because 3 times 2 will give me 6. Whatever I do to the bottom of the fraction, I have to do the same to the top. So up top here, I'm going to have 15 plus 14. I can simplify my numerator. This will be 29 over 6x plus 4. If I could factor and cancel, I would, but in this case I don't. Right? If this was a 24, I could simplify it, but I can't. So that's my final answer. In this last problem, we have a complex fraction, which means it's a fraction in a fraction. So we don't want a complex fraction, so we want to get rid of all of these denominators. So we want to find a value that's going to cancel out all of these denominators. So I want a value that's going to cancel out 6, x squared, 6x, and x squared. So really what it's called is my LCD. I want to multiply everything by the LCD 6x squared. So I'm going to write that near all of them. Well, this I don't have a lot of room here. And 6x squared. And now, this is really like over 1 here. So I could cancel out 6 and 6. Those would be gone. And I'd be left with x squared times 1. And here my x squared will cancel out with my x squared. And I'd have 6 times 6, 36. No longer have any fractions. Down here I want to do the same. I'm going to cancel out my 6 and 6. Leaves me x squared times 1 is x squared. Here I have a 6x squared. Remember, it's up top there. And I have an x down here. So one of my x's will cancel out with one of my x's. I'm left with 2 times 6x, which looks like a positive 12x. My x squares cancel out there. Gives me my 36. I no longer have a complex fraction. All my denominators have canceled out. So now I could simplify this. All I have to do is factor the top and factor the bottom. X plus 6, x minus 6, the difference of two perfect squares. And at the bottom, this is a perfect square trinomial. 6 and 6 gives me 36, and they're both positive. I factor completely, and then I can cancel out my like factors. So I could take out this x plus 6 and x plus 6, leaving me with x minus 6 over x plus 6. My final answer. And that's it. The end.